Hi, I'm Teodora. I'm a PhD student at NUS School of Computing, and I'm working at the intersection of security, formal methods, and machine learning. Today, we'll be talking about our work on quantitative verification of neural networks and its security applications. This is joint work with Shichi Shweta and my PhD advisors, Kuldeep and Pratik. This work was published at CCS 2019, so do check out our paper for more details. So let's start with neural networks and more broadly, machine learning systems. Today, these are prevalent everywhere. However, their wide deployment raises different kinds of concerns. When we use these systems in predicting loan eligibility or criminal sentencing, we're interested in making sure that certain criteria of fairness are enforced. For example, that it does not discriminate based on race. Another important concern is related to robustness and safety of these systems, as it was shown that neural networks are prone to adversarial examples. An adversary given white box or even black box access to the neural network can craft adversarial examples, that is, images where a small imperceptible change makes the neural network mispredict. This can have tragic consequences and has had tragic consequences for self-driving cars. Another type of attack with dire consequences are data poisoning attacks, and here we mention trojaning attacks, where the attacker can introduce their own malicious data in the training set such that the model can predict a target label when a certain pattern that the attacker chooses is present. If we are to widely deploy these systems, we want to have solid guarantees about their fairness, robustness, safety, and susceptibility to trojaning attacks. Thus, the research community has been looking at verifying properties of neural networks. And the classic approach to design a verifier is that given a specification for a property P and a neural network N, the verifier can output true if the property holds for all inputs or false if it doesn't, and produce a counterexample. This approach works well for properties such as safety and robustness, and there is significant progress in recent years in the development of such verifiers. However, this may not be the case for all kinds of properties. So let's look at the fairness property. Say we have a neural network that predicts whether an individual is eligible for a bank loan. While there are countless definitions of fairness, here we will be looking at individual fairness, where similar people will have similar outcomes with respect to a classification problem. In particular, the question that we ask is whether two individuals with different sex but same income, education, etc. get the same prediction. Here we can have other kinds of sensitive features like race or nationality, etc. Let's say we use a verifier for the given neural network and this property. Now, if the property is true, that's great news. We have found a perfectly fair classifier. Now, if the property is false, however, then the verifier produces a counterexample and the concrete input to the neural network where changing the sensitive feature results to changing the prediction. So here we had a concrete example where changing the attribute from male to female leads to the bank loan being denied from approved. So it turns out that due to the stochasticity in the training, it is unlikely that we are in this ideal scenario where the neural network is perfectly fair. To be fair to the designers of neural networks, the accuracy is rarely 100%. So once the verifier has produced a counterexample, we don't really know how fair is the actual neural network on the rest of the inputs. Or said in a different way, if we have two neural networks that have similar accuracies, can we pick the one that is more fair? So to answer these questions, we introduce quantitative verification, where given a property P and a neural network N, we answer how often P holds for N. So instead of a binary yes or no answer, we produce a count of how often. This actually is the first contribution of this work, where we propose a novel notion of quantitative verification. Our second contribution is that we produce these estimates with soundness guarantees. And the third contribution is that we provide an efficient procedure for a type of neural networks called binarized neural networks. And we implemented in a tool called NPAQ, which stands for Neural Property Approximate Quantifier, 3 different security applications: fairness, robustness, and Trojan attacks, and evaluated our tool on these applications. So let's see what soundness means in this context of quantitative verification. So here, whenever we produce an estimate, here R hat, we want this estimate to be within a multiplicative error of the ground truth R. So here epsilon is the tolerance, the error tolerance that we want to admit. And we want to produce this estimate with a probability higher than 1 minus delta, which delta is the confidence parameter. These are called probably approximately correct or epsilon delta style guarantees. So now that we have defined our goal to produce sound estimates, how can one go about estimating how often P holds for N? So let's go back to our neural network with 100 binary features that predicts whether an individual gets a loan. So one way to go about it is to look at the neural network as a black box and sample and observe the outputs. Say we randomly generate pairs of inputs that differ only in the sensitive feature. So the first feature is the sensitive feature. And then we observe the outputs. So say we have randomly generated these 2 vectors, and now we just have to run it through the black box and observe the output. So for the first vector, we see approved. For the second one, we see denied, and we have actually found a counterexample. However, the worst case for this approach is that we might have to do 2 raised to 99 checks or a very large number of checks if the event of finding such examples is rare. The alternative to this approach is to reduce the problem to model counting, or sharp SAT. Given a neural network N and a property P, we this time encode a specification phi of the problem of how often P holds for N, and we use a model counting to find the number of satisfying assignments for this specification. However, there is no free lunch. Counting is actually a very hard problem. It's in fact Sharpie complete, and even its approximate variant is NP hard. But existing approximate counting tools have seen great improvements in recent years, which gives us hope. So we actually relax our problem to approximate model counting. So here, the tools work with Boolean formulas in CNF, in conjunctive normal form, and give us the epsilon delta guarantees that we want. However, the challenge is, how do we obtain a specification in CNF? In particular, we will look at a type of neural networks called binarized neural networks, and we will open the black box and look at how we can actually obtain that specification. So first of all, what are binarized neural networks? Binarized neural networks are a type of feed-forward neural networks with binary weights and sign activation functions. So more specifically, it takes as input a binary set of features. It goes through a linear layer, then a batch normalization layer, and then goes through the activation. These 3 transformations make up an internal block, and the binarized neural network can be made up of several of these internal blocks. And at the output, it will have a linear layer followed by an argmax, and this is the output block. However, for the purpose of this presentation, let's just consider the first neuron of the first internal block. And this is just a very simple transformation. I put here the transformations on the right side, but it's but this example will be very simple. So here the weights are all 1s, the bias is 90, and the batch normalization transformation is actually an identity function. So these are the parameters. And in the end, we will obtain these 2 equations for corresponding to the behavior of the first neuron. So observe that it's just a sum over the input features plus the bias. And if the sum is greater than 0, then the output is 1, otherwise it's -1. However, because we want to obtain in CNF, we have to first get rid of the binary variables and convert them to Boolean. So we convert them to Boolean using this formula, and then we obtain this kind of constraint. So let's just look at the left side. How do we go about encoding this to CNF? So let's call this formula C. So one way to do it is to encode all combinations of 5 or more variables cannot be set true at the same time. So this results in 100 choose 5, which is more than clauses, which is more than a million 10 raised to 7 clauses. So encoding, so this is just for one neural network, so you can imagine one neuron, so you can imagine for the whole neural network it will be a very, very large intractable encoding. This kind of encodings are called equivalent encodings because you keep the same variables. However, in the logic community, people have developed since a long time this idea of introducing auxiliary variables for subformulas. So the formula C becomes F, where F has these auxiliary variables. These are actually transformations that preserve a certain property, which is equisatisfiability. So if C is satisfiable, then F is satisfiable, and if F is satisfiable, then C is satisfiable. So this kind of encodings there's a lot of these kinds of encodings when you work with things like SAT and SMT solvers. So now we have the formula C on variables Z1 to Z100, and we have the formula F, which contains these auxiliary variables. But the question, even if the satisfiability is preserved, what happens to the count, to the number of satisfying assignments of these two formulas? So it turns out that we can actually obtain the satisfying assignments, the number of satisfying assignments, by projecting on the Z variables. And we formalize this into a concept called equicardinality. So we want to preserve the number of satisfying assignments. So if the transformation is sound, then this property is preserved. So if C is equicardinal to F, then the number of solutions for the input variables is preserved. All in all, this gives us a quantitative verification where, given a neural network N and a property P, we obtain a specification phi in CNF where we ensure that the transformation is equicardinal. That is, we preserve the number of satisfying assignments. And then we use an off-the-shelf approximate model counting tool, which has the epsilon delta guarantees for our soundness guarantees. So now let's take a look at applications. So for the fairness application, we concretely to train binarized neural networks on the UCI adult data set, where they predict if the annual income is higher than a threshold. So you can think of it as if it's higher than a threshold, they get the individual can get a bank loan. After getting rid of redundant features and cleaning up the data set, we were left with 66 binary features. So here P1 encodes the fairness property that we discussed throughout the presentation. So the first conjunction is over all of the features except the first one, which is the sensitive feature. So we want to keep all of these features exactly the same. However, the first feature is different. So this one is male, the other one is female. And the prediction is the same. So here we're actually encoding how often is the fairness how often is this classifier fair, or how often is this fairness criteria correct for the given neural network. So this is one kind of property that we can encode with this criteria, but we can also take it one step further and encode if the direction of unfairness. So let's say if how many inputs which are male and are approved would otherwise be denied if they were female. That's the second property. for the third property, it's vice versa. So if all of the features are kept the same, but if the individual is male but was denied, what would happen if the individual were female, and how many of these individuals would have their bank loan approved? So using our tool, NPAC, we can actually we actually experimented with 4 kinds of binarized neural networks with 4 different architectures, and with this encoded these 3 properties, and we can actually obtain some estimates within 6 hours. So here we used an epsilon of 0.1 and a delta of 0.1, but this can be set to anything that the user desires. And now we can get estimates for how often these neural networks are fair, and we can potentially choose the one that suits the application better. So here the results are ratios. So it's basically the number of satisfying assignments over the total input space. The second application that we looked at is robustness. So while there is definitely space for the classical verification of robustness, here we're looking at robustness from the point of where we want to compare the robustness of different models. So robustness, as I mentioned in the beginning, is when the attacker can introduce an imperceptible change. So here the imperceptible change is 2 pixels change, and the neural network misclassified from 0 to 8. And the way to encode this is we want to make sure that the number of bits that we changed is under k, and the output of the classifiers are the classifier changes. So here I remind you that we are dealing with binary input features. So actually the pixels are -1, 1. So that's why we can directly encode it like this with XORs. So now we can actually compare models. So here we actually took plain binarized neural networks, and we used 2 different defenses to harden the binarized neural networks. And we asked which neural network has less adversarial examples among these 4 models and their hardened versions. So again, we are able to estimate how often this happens within 24 hours. And here you can have a comparison. So again, here we show the utility of NPAC, but of course the results will differ on the application and everything. So it turned out that the plain neural network the plain binarized neural network was in most cases more robust, but that will depend on the actual neural network that you've trained. So with this, I would like to end my talk, and thank you for your attention. We have proposed a novel notion of quantitative verification, which is sound and efficient in terms of the neural network parameters. We show its application to fairness, robustness, and Trojan attack success. And currently, the NPAC can scale to binarized neural networks with 50,000 parameters. And there's definitely future work to improve its scalability and also extend it to other types of networks. Thank you for your attention.